So in this video, we'll be performing a torque balance for a Couette viscometer. So I've drawn a little diagram here of a Couette viscometer with a large cylinder right here, and then a smaller cylinder inside of that, and some fluid in between right here, and there will be a little air pocket right here at the bottom of this inner cylinder. So basically what we're trying to find is that there is a motor attached here to this inner cylinder that will exert some torque on that cylinder, and that torque on that cylinder will agitate this liquid because it has viscosity, and then that liquid will exert torque on this outer cylinder. And what we're trying to figure out is we're trying to balance those two torques and prove that they are actually the same. So a couple more things that we need to keep in mind is that the height of both these cylinders will be h, and then the radius of the inner circle is going to be little r I, and then the radius of the large circle is going to be big R. So then right here, there are just a few equations that we were given to start this problem. So first, this is our shear rate is going to be equal to some radius. This isn't our inner or outer radius, it's just some radius in that range. And then the derivative with respect to that same radius with our velocity profile divided by that radius as well is equal to our shear rate. And then our velocity profile here is going to be equal to the angular velocity times k squared, and our k here is just some constant ratio right here of our inner radius to our outer radius right here. So k squared over 1 minus k squared, and then our outer radius squared divided by, again, just some radius. This isn't our inner radius. We're eventually going to be plugging in our inner and outer radius for this radius. So this is just an arbitrary r. So it's our big radius squared over r minus r, the same radius. So now we can start this off by talking about Newton's law of viscosity. And what that states is that our shear stress is going to be equal to our shear rate times the viscosity. Now, one thing we also know is that this shear stress is going to be equal to our force divided by the area of the cylinder. So now we can multiply by our area on both sides and get force by itself on the left. And now finally we can input our torque. So as we all know, the basic equation for torque is going to just be torque equals force times motor arm. And our motor arm in this case is radius. So our torque, I'm just going to write it really small right here. Our torque will be equal to our force times R. So obviously I can input that into here. We're just going to multiply both sides by R. So we'll end up getting that our torque is equal to our viscosity times the shear rate times the area times the radius. And this equation here is going to be really important once we start doing our torque balance, obviously. So I'm going to erase all this and recopy this up here. Torque will be equal to the viscosity times our shear rate times the area times that radius. So obviously that area will be changing depending on which torque we are looking for, the inner cylinder or the outer cylinder from the liquid. And obviously that R will be changing too, but we will input all that later. So now what we need to do is find an equation for this shear rate that we can substitute in to this torque equation. So obviously we have this here, but it has our velocity profile divided by R inside this derivative. So first what we're going to do is just divide our velocity profile by R. So that's going to be our velocity profile divided by R, and this whole part is going to be the same. It doesn't have an R in it, so it'll just be k squared over 1 minus k squared, and then we're going to divide this by R, so it'll be big R squared over little r squared minus little r over little r, so just minus 1. And now all we have to do is take the derivative of this with respect to R. So that'll be d over dr of velocity profile over R is equal to, and again this is all a constant, so it will not change because of the derivative. And then now, so the derivative of 1 here, it's just constant, so we'll just go to 0. And then here, this big R squared is also just a constant, so that'll stay the same. And then the derivative of R to the negative 2, again, you just subtract 1, so it'll be R to the negative 3, but then multiply by negative 2 out front, negative 2. And then now, all we have to do is multiply by R here. So R d over dr will equal, all this will stay the same. And then we'll just take 1 off, 1 R off down here. So big AR squared over little r squared. So now we will have an equation for our shear rate at some radius r. So I'm going to write that down here. our shear rate for some radius r will be equal to -2 omega k squared over 1 minus k squared multiplied by big R squared over little r squared. And now I can erase all this. And now finally, all we are going to have to do is just plug in this equation for each of our outer cylinder radius and inner cylinder radius and solve for the torque and see if they are equal to each other. So first we're going to solve for the torque on the inner cylinder from the motor up there. So the torque on the inner cylinder is going to be equal to, and we're just going to use this here, so viscosity times our shear rate at the inner radius. So if we plug that in here, we're going to be plugging it in for this r here. So it'll be r squared over ri squared. And as we can see here, that'll just be the inverse of our k. So we can say that that'll be k to the -2, and these will cancel. So we'll just end up with -2 omega over 1 minus k squared. And then we will just have our area, which will be 2 pi ri times the height and then ri, our radius again. So that will be the torque for the inner cylinder. And then now we are going to solve for the torque for the outer cylinder, which again we're going to use this equation that we derived here. So again, just be the viscosity. And then now for our shear rate, we're going to be plugging in big R. So this will just cancel, since it'll be big R squared over big R squared. So then we'll just have -2 omega k squared over 1 minus k squared. And then our area, which this time will be 2 pi big R h, and then multiplied by big R. And now, to prove that these are in fact equal, I'm going to set them equal to each other. So we'll have mu -2 omega over 1 minus k squared 2 pi ri h ri equal to our viscosity again, -2 omega k squared over 1 minus k squared 2 pi big R h r. So now we can just cancel everything that is the same. So the viscosities will cancel, our -2 omega will cancel, 1 minus k squared will cancel, or 2 pi's will cancel. And I'm going to rewrite it like this first. So Ri h times Ri will equal k squared times big R h times big R. So the h's will cancel as well, and we will get Ri squared is equal to k squared big R squared. And now finally we can plug in our k equation here. So we'll get that, we'll get that Ri squared is equal to Ri squared over big R squared times big R squared. So these will cancel, and we get that Ri squared is equal to Ri squared. So that checks out, and we have performed our torque balance for a Couette viscometer.